All right, let's look at vertical circles and kind of analyze what's going on here. So we have a ball that's basically spinning in a circle, clockwise. Um, and it's whirled vertically. So that vertical component is important. The important thing is that it is hung vertically. So then when we get to part A, it says cross out the incorrect statements from each student's argument. So Dominique says the net force on the ball at the top position is 7 newtons since the net force is the same as the tension. That is not true. Um, sorry, I don't need to erase everything. They say the tension in the cord at the top is 7 newtons. The tension in the cord at the bottom is 7 newtons. So the net force is not the same as the tension because we know that there's tension and gravity pulling on it. So that can't be true. We also know, therefore, that the net force is not 7 newtons because they only tell us the 7 newtons. So everything about Dominique's statement, unfortunately, is incorrect. Carlos says, no, the net force on the ball includes the centripetal force, tension, and weight. So this is incorrect in that there is no such force when we're talking about all the individual components as the centripetal force. Remember, that's a descriptor that applies on top of whatever is providing the force. So at the top, you only have tension and weight. So the tension and weight are acting downwards and have to be added. That's fine, that's correct. Both tension and weight are pulling it downwards, or in other words, tension and gravitational force. Then you need to figure out the centripetal force, mv squared over r, and include it in the net force. That is not true. We do not want centripetal force added in. Instead, we know that the centripetal force will equal the sum of the tension and the weight. So in the few short sentences, state the net force at the top and support your claim with evidence. So Carlos is right. It is the tension plus the weight. It's also equal to, let me write that, Ft plus Fw, which is also equal to Fc, which is also equal to mv squared over r. So explain that in sentences if you were doing this yourself. So it is the tension and the weight because those are the two forces pulling on it. There's nothing else acting on it. But we know because it's traveling in a circle that that net force must be equal to the centripetal force, which must be equal to mv squared over r. So if you do that, you'll know that it's 7 newtons plus 2 newtons, which is 9. Because if you look up here, the weight is 2, and the tension at the top is 7. Then down here, we have using representations. The diagram at the right shows the circular path of the ball from part A. The dots below represent the ball at marked locations. Draw the free body diagram showing the forces, and draw the relative lengths of vectors to reflect the magnitude of forces, magnitude of all the forces. So in every case, we know we're going to have some Fg pointed downwards. And Fg never changes. It's always the same amount. So we can draw those in like so. Drawing it small just so I've got space to make things bigger and smaller. Now, Fp and Fm are both experiencing some tension force towards the center. So Fp, we're going to do like this, tension force. And Fm, we're going to do tension force like that. These are the same. Now, when we get to the top, we don't need quite as much tension force because we need a total of, let's say this is, if we're at the top 7, 9, we'll say that this is 9 newtons right here. At the top, we don't quite need the full 9 newtons because some of it's provided by the gravitational force, right? Up here, some gravitational, some tension to provide the total that we need, the total centripetal force required. So this right here will be less than the tension force. Let me write that here. Ftz is less than FTM, which is equal to FTP. The tension force at the top is less than the other two because it's got gravity pulling it towards the center as well. Conversely, at the bottom, FT has to be bigger because it's got to counteract gravity and provide all the centripetal force. So that's why we see here, we see that we've got at the top of the path the least amount of tension, the bottom of the path the most amount of tension, and at the two kind of horizontal all the way out to the sides, it's got exactly as much as required to make it go in a circle. So quantitative analysis, let's do some math here. So the net force is equal to MAC. That means the net force is also equal to V squared over R. They were asking for the speed at point Z, which is the top. So we know that that will be Ft minus Fg is equal to mv squared over r. And we know that we would have, so this is replace centripetal acceleration of v squared over r. Here we know that net force is tension minus Fg. Now, if we want the minimum speed, that would be when the speed at which all of the centripetal acceleration is provided by gravity. So in other words, Ft would be equal to 0. Meaning we have just, if we're still staying in a circular path, we can't get rid of Fg. But we can reduce the Ft. So net force is, actually if we're at the top, we'd want to have these be pluses, sorry. The Ft equals 0 for minimum speed. And that means that we get v squared, and sorry, you can also say this is mg if you want. Don't worry too much about the number of boxes here. It's just a way to kind of tell you there should be a couple of steps or a lot of steps. And then that gives us, if we algebraically rearrange that, v is equal to the square root of g times r. And that's just algebraic rearrangement. Suppose the string breaks at point P. Describe the motion of the ball after the string breaks. When describing the motion of an object, you discuss what happening to the position, velocity, acceleration. Tell the story from the time the string breaks to the ball hitting the ground. So position, point P was at the side when it was going up. Increases to max height. Then falls. And it only moves vertically. And then velocity decreases until max height. Turns around, then increases, at the max height, the velocity is 0, then increases until hitting ground. And the acceleration is a constant 9.8 meters per second squared. And that's just because, it's in free fall. It's the gravitational acceleration. All right, looking at this next scenario, we've got the car at the top of the hill. Draw a free body diagram showing the forces, not the components, and draw the relative lengths of vectors. So in this case, we've got gravity pulling it down. And assuming that the car is not passing over at the maximum speed that it can, there will be some upwards normal force. But in this case, it won't be equal to the gravitational force because we ultimately need a net force downwards to provide the centripetal acceleration to make it go in a circle. So we do know that it has to be less than Fg. If the car was moving as fast as it could possibly go without leaving the ground, then Fn would be 0 at that moment. But because they don't tell us that, we're going to assume it's some amount that's non-zero. So derive an expression for maximum speed. This is where we'll actually, though, look at that aspect of the fastest we can go. So the net force is equal to Fg minus Fn, because they're pointed in opposite directions. So that will equal mv squared over r, because we can also replace the AC with the v squared over r. In this case, the maximum speed, we want to have the normal force be 0, because again, we can't reduce gravity at all. Gravity is what we have if we want to work on it. If we're going slower, then we'll need kind of normal force to stop us from falling into the ground. So that will equal our mv squared over r. That means that we have Fg is equal to mv squared over r. Fg is the same as mg. And then we can do some algebraic rearrangement to get v equals the square root of g over r. And this is exactly the same as what we looked at before in the previous lesson, but instead of having tension providing that centripetal force, now we have the normal force kind of allowing us to go slower. So when you're spinning something in a circle, there's a minimum speed that you can do, because in other words, you have to, you're pulling in with a minimum amount of force. When you're driving over something, there's, a maximum amount of force that can be provided. The max amount of force that can be provided is Fg. When you're trying to pull in, the minimum amount of force you can pull in is Fg. So if you want something to be, spinning, and you want to be able to spin it faster and faster arbitrarily, you need to be pulling on it in a way that you can change that pull, or pushing down on it in a way that you can push. If you're trying to have a minimum speed that you have to move with, then you want an outward force. In the derivation, explain why you set normal force equal to 0. Again, the idea here is if we want to find the maximum speed, normal force is only going to reduce the speed we can travel at. Because the normal force means there's less centripetal force. Less centripetal force means that you can't move with as high of a speed. So we want to have the maximum amount of centripetal force, which means we want the minimum normal force. A truck of mass 2m passes over the same bump. Compared to your car, how many times bigger or smaller is its maximum speed? It's exactly the same, because again, up here, there's no mass dependence. So that's the idea behind these two kind of vertical circles. Play with it some more, ask questions if you have it, and we can work through those as they come up.